Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to look at the method of successive parabolic interpolations for finding extrema of a real valued function of a real variable. So in this topic we will describe the method of successive parabolic interpolations for finding an extrema. We will find a formula for the next point that is less subject to subtractive cancellation than the general formula. We'll also look at an example. Recall the secant method. In this method, given 2 points, we let the next approximation of the root be the root of the interpolating linear polynomial that passes through these 2 points. Well, a straight line does not have an extrema. However, a parabola does. So, given 3 points instead of 2, let the next point that is approximating the extremum of the function be the extrema of the interpolating quadratic polynomial of those 3 points. So, for example, suppose that we have 3 approximations of a minimum of a particular function, and we've evaluated the function at these 3 points. We find the interpolating quadratic that passes through these 3 points, and therefore our next approximation of the extremum of the function would be, of course, the minimum, in this case, of this interpolating quadratic. Consequently, what would we do now? We'd probably discard x sub k minus 2 and continue iterating with these 3 points. Well, not really. What we would actually do is we would evaluate x k plus 1 at the function at that point, and then carry on finding the interpolating polynomial through those points. Now, given 3 initial approximations, x0, x1, and x2, then we start iterating. So consequently, given the last 3 values, x sub k minus 1, and x sub k minus 2, we find the interpolating quadratic that passes through these points, and that would be of the form a times x squared plus bx plus c. And we can find the value of a with this formula. Now this formula is a little bit more complex than previous interpolating quadratics because the points are not necessarily equally spaced. Now, having calculated a, if a is greater than 0, then the extrema of this quadratic polynomial is a local minimum. If a is less than 0, it's a local maximum. And if a is equal to 0, then we have to examine the slope. Now, if the slope is 0, then, or very close to 0, then we are likely to be very close to an extremum. And we can calculate the slope using this formula if necessary. Now, from calculus, you know that the minimum of the polynomial ax squared plus bx plus c is at the point x is equal to negative b over 2a. So using the 2 previous expressions and simplifying, we can calculate the next approximation being this reasonably complex expression here. Again, it's more complex because the points are not necessarily equally spaced. Now, question, is there anything that we can do here to reduce subtractive cancellation? After all, a lot of these values are going to be very similar. Well, the first thing we're going to do is at every single step, we're actually going to rearrange the previous 3 points so that the most recent is also the one that has the least value. The second most recent has the next smallest value, and so on and so forth. And so at every single step, the most recent point, x sub k, will be the one that is smallest. All right, so now let's recall that the minimum of a function is also the minimum of that function minus a constant. So given these three values, what we could actually do is subtract off of each of these three values the value f at x sub k minus 1. That would give us these 3 points here for which we are finding the minimum. Okay, so if we subtract off f at x sub k minus 1 from each of the f values in the previous expression and simplify, we now get this expression here, which is ever so slightly simpler than the previous one. Now there's something that's very nice here. We've actually calculated some of these values previously when we were finding the coefficient a. So this is good. Less work for us to do. However, on top of all of this, we can also factor out the average of the last 2 points out of this expression, given this even simpler expression. You will also notice that, after all, if x sub k and x sub k minus 1 are the two smallest values, chances are the minimum of the interpolating quadratic will be close to one of these two values. Consequently, the expression on the right should be reasonably small. Also, in the numerator, you have a difference of the value of the function times two differences of the x values, whereas each of the terms in the denominator are simply a difference of the values of the functions times a difference of the two x values. So consequently, the expression should indeed be reasonably small. Now question, having found the next point x sub k plus 1, which point do we discard? Well, first of all, if perchance f evaluated at x sub k plus 1 is actually greater than f at x sub k minus 2, then we have a serious issue. After all, this means that either we didn't start sufficiently close enough to a minimum for this technique to converge, or alternatively, the function is not sufficiently well behaved, meaning it is not continuous and sufficiently differentiable. That is, it isn't truly a quadratic locally around the minimum. However, assuming this is not the case, recall that f at x sub k was indeed the smallest of the previous three values. We're going to then check if the difference between the two f values is sufficiently small and the difference between the step size is also sufficiently small. We're more or less finished. Return either x sub k or x sub k plus 1, whichever has a smaller value. Otherwise, discard x sub k minus 2, as that is the largest f value and we are finding a minimum, and proceed on with x sub k minus 1, x sub k, and our newly found x sub k plus 1. The rate of convergence of this algorithm is superlinear and appears to be on the order of h to the 1.3247, where h is the error of the previous most recent estimate. Now, interestingly enough, this value appears to be very close to the real root of the polynomial x cubed minus x minus 1, and you'll recall that the convergence of the secant method was order h to the phi, where phi is the golden ratio, and the golden ratio itself was a root of the quadratic x squared minus x minus 1. So the root of this cubic is specifically this value here, which is, again, very close to what is actually observed. All right, let's apply this method of successively finding interpolating parabolas in order to estimate a minimum for this particular function 2e to the negative 2x minus e to the negative x. And we're going to assume that the minimum is on the interval from 1 to 2. Now the actual minimum is at x is equal to 1.38629 and change. And at this point, the function finds a minimum value of negative 0.125 exactly. So starting with 3 equally spaced points, we can evaluate the function at these 3 points, and using our formulas, we can find the minimum of the interpolating quadratic. And it is at the point x is equal to 1.5073 and change. Now, looking at the 3 values we started with, the one that has the largest value of the function is x is equal to 1. So f at the other two, evaluated at the other 2 points, has a value that is more negative. So we will discard x is equal to 1 and replace it with x is equal to 1.5073 and change. All right, now we have these 3 points. We'll find the interpolating quadratic, and the minimum of that interpolating quadratic is at x is equal to 1.2619 and change. All right, so once again, we look at the 3 points and we see that at x equals 2, that is the largest value of the function, and therefore we will discard x is equal to 2 and continue iterating with 1.2619 and change, 1.5, and 1.5073. So once again, find the interpolating quadratic, find the minimum of that interpolating quadratic, and it is at this point. At this point, we can now discard the first point again, and we continue. We find the interpolating quadratic. It has a minimum at this point, and looking at the various points, we note that we can now eliminate the third point. X is equal to 1.5073 and change. And once again, we can evaluate the function at this point, and we note that the value of the function is negative 0.12499, which is pretty close to what we know the minimum is, so we can trust this technique. Finding the minimum of the interpolating quadratic of these 3 points gives us this point here, and incidentally, the value of the function at this point is actually very close to the overall minimum. Once again, note that the point 1.38635 is not that close to the actual minimum, but the value of the function at this approximation is actually close to the minimal value, which is negative 0.125. Following this topic, you are now aware of the method of successive parabolic interpolations. And this is a technique that is very similar to the secant method. You also understand that it's possible to calculate the next point with less likelihood of subtractive cancellation. You know that this technique has superlinear convergence, and you now have seen an example of the application of this technique. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!